subtracting and multiplying a matrix by a single value. And then in the next section, 3.2, we will talk about multiplying two matrices. And then in section 3.3, we will talk about taking the inverse of a matrix. For various reasons, we cannot divide two matrices by each other, but instead of dividing two matrices by each other, we multiply one by the inverse of the other one. So it's important for us to know how to find the inverse of a matrix, which we will do in section 3.3. So once again, in this section, we will talk about adding, subtracting matrices, and multiplying matrix by a single value. In section 3.2, we will talk about multiplying matrices by each other, and in section 3.3, we will talk about finding the inverse of a matrix. Okay, so the first thing we need to know before we get on this journey is that what is the dimension of a matrix? So that's the first thing we need to know. Dimension of a matrix is usually expressed by m, by these letters in various books, m times n. Whenever you see this, the first number always represents the number of rows in a matrix, and the second number represents the number of columns. So if you have a matrix that is like this, so let me box this. So if you have 1, 5, 7, negative 3, so the dimension of this matrix, the rows, there are 2 rows and 2 columns. So 2 by 2. That's the dimension of that matrix. If you have a matrix like this, 3, negative 8, 1, and 2, and then 4, 6, 7, and 3, the dimension of a matrix is 2 by 1, 2, 3, 4 columns. So 2 by 4. 2 by 4. If you have a matrix like this, this matrix has dimensions 4 by 1. 4 by 1, right? 4 rows, 1, 2, 3, 4 rows, and 1 column. On the other side, if you have a matrix that is like that, the dimension of this matrix is 1 by 3 columns, right? 1 row and 3 columns. Of all of these 4 examples that I'm showing here, only one is what we call a square matrix, that one. Square matrices are matrices that have equal number of rows and columns. So these are not square matrices, as you can see. Another square matrix, let me give another example here. And this is another square matrix. And the dimensions of this matrix here are 3 by 3. I'm sure you can see that. So 3 rows, and 3 columns. When we get to section 3.3, which I've already mentioned, we talk about finding the inverse of a matrices. So only square matrices have an inverse. So you already know that this matrix and the other one, these do not have inverse matrices. Only square matrices have an inverse. And not all square matrices have an inverse. But if a matrix has an inverse, that matrix must be a square matrix. But not all square matrices have an inverse. Keep that in mind. We will talk about it when we get to section 3.3. But at this point, the important thing is that you know how to write the dimension of a matrix. Okay, so since we now know what the dimension of a matrix is, here's a very important note. Only if two matrices or more have the same exact dimension, we can add or subtract them. Okay, that's a very important thing to keep in mind. So let's, so for example, we can say, for example, the operation this operation 3 minus 1 5 2 minus 2 minus 6 5 4 1 3 cannot be performed. Okay, because these two matrices do not have the same dimension. This one is a 2 by 2 matrix. This one is a 2 by 3 matrix, so we cannot subtract them like this example is saying. Okay, so now that we know that, let's focus on examples where we can add or subtract matrices. So here's an example. We want to add this matrix to that one. Well, they're both 2 by 2, right? This is a 2 by 2, this is a 2 by 2, so we can add these. So 3 plus negative 2 is 1, minus 1 plus 2 is 1, 4 plus 2, 6, 2 plus 5, 7. So I'm sure you were able to follow and see that I'm adding the elements in the same position, right? So that's how we do that. Let's do another example. It's going to be a little bit different than this. We want to perform this operation 6 times. So this is, we're multiplying the matrix by a single digit. 6 times this matrix like that. Okay, so here all we have to do is distribute this number in front to every element in the matrix, then distribute the 4 into every number in the matrix, and then add the two matrices. So here's what I mean. So 6 times 2 is 12, 6 times 1 is 6, 6 times 3 is 18, 6 times 1 is 6, 6 times minus 1 is minus 6, 6 times 0 is 0, plus, now let's distribute the 4. 4 times 6 is 24. 4 times negative 4 is negative 16. 4 times negative 2 is negative 8. 4 times negative 3 is negative 12. 4 times 0 is 0, 4 times 1 is 4. So we're just done distributing the constants. But now we have to add the elements. So 12 plus 24, we have 36. 6 plus minus 16, that's minus 10. 18 plus negative 8, 10, or positive 10. 6 plus negative 12, negative 6. Negative 6 plus 0, negative 6. 0 plus 4 is 4. Okay, so let's see another example. This time we're going to subtract. Suppose we want to multiply this 2 by this matrix. Okay, that's what we want to do. Okay, just like before, let's multiply this 2 by everything here. So 2 times 1 is 2, 2 times negative 1 is negative 2, 2 times 8 is 16, 2 times 2 is 4, 2 times 4 is 8, 2 times 1 is 2. Now here, once you get to this, you can either keep the negative here, keep the subtraction symbol here, and distribute just the 3. You can do that. Or you can multiply the negative 3 and convert this to an addition. I think I found it, you might not agree with this, but I found it that it's easier if you distribute the negative 3 into everything and then simply add the matrices rather than subtract the 2 matrices. Okay, so that's what I'm going to do. So I'm going to convert this to positive, but that means I have to distribute the negative 3 to everything. Negative 3 times 0 is 0. Negative 3 times negative 2 is positive 6. Negative 3 times 8 is negative 24. Negative 3 times 1 is negative 3. Negative 3 times 4 is negative 12. Negative 3 times 1 is negative 3. Okay, so now we can add the matrices. That's always easier than subtracting the matrices. So saying, if I had not distributed the minus 3, if I had distributed just the 3 and kept the negative, now I would have to subtract, and I would say 2 minus 0, minus 2 minus 6, 16 minus minus 12. That's always more difficult than adding matrices. So that's why I distributed this negative 3 from the outset. So now all I have to do is add the numbers, not subtract them. Okay, so we have 2 plus 0 is 2. Minus 2 plus 6 is 4. 16 plus negative 24 is negative 8. 4 plus negative 3 is 1. 8 plus negative 12 is negative 4. 2 plus negative 3 is negative 1. Okay, so this is the result of that. Now let's look at operations that involve matrices that have variables in them. So let's see how that's going to work out. So suppose we want to do this. Suppose we want to multiply the 2 to this matrix where it has 2x, 6y minus z, x, 9y, 5z, and then minus 3x, y, 2z, 7x, 4y, minus 6z. Okay, so here I'm going to distribute the 2 first. We will have 4x, 12y, minus 2z, 2x, 18y, 10z. When I get here, once again, I prefer to distribute the negative and then add the matrices rather than keep it like this and say 4x minus 3x. You can do that if you want, but I'd rather add rather than subtract. So I'm going to convert this to add, and then I'm going to distribute this. Minus 3x, minus y, minus 2z, minus 7x, minus 4y, positive 6z, right? Okay, now I'm going to add these 2 matrices. So we have 4x plus minus 3x, that's just x. 12y plus minus y, that's just 11y. Minus 2z plus minus 2z, that's minus 4z. Two x plus minus 7x, that's minus 5x. 18y plus minus 4y, that's positive 14y. 10z plus 6z, and that's 16z. Okay, so that looks all right, like that. Let's do one more example, and then we'll wrap up this section. So in this example, suppose we want to find x and y so that these 2 matrices are equal to each other. So x minus 6y 0, minus 6, 42. Like that. So we want to, in this equation of matrices, our objective is to find x and y such that the 2 matrices are equal. Well, if the 2 matrices are to be equal to each other, their equivalent elements should be equal to each other. So 0 is equal to 0, minus 6 equals to minus 6. Let's set this equal to 7, and x plus y equal to 42. Okay, so we're going to have this system. X minus 6y equals 7. Then x plus y equals 42. If these 2 matrices are to be equal to each other, we must have this system solved for x and y. Okay, so let's do that. This is an easy system to solve. We can simply multiply the top equation by -1 to get rid of the x terms, and then solve for y and plug back in and solve for x. So minus x plus 6y equals minus 7. X plus y equals 42. Let's add these 2. The x terms drop out, right? 6y plus y, that's 7y, equals minus 7 plus 42, that's positive 35. So y is equal to 35 over 7, and y equals to 5, right? That's y. Let's find x. So we can, using any of these original equations, we can solve for y, solve for x. So using the easier one, x plus y equals 42, we have x plus 5, right? Plus 5 that we just figured out from here equals 42. So then x, x equals 42 minus 5, x equals 37. Okay, so we have the y, we have the x, then the x and y values are 37, 5. Okay, with this, we have wrapped up section 3.1. And when we come back next time, we will begin with section 3.2, which is about multiplying matrices. So that's quite a different method than what we've talked about in this section. That's why it gets its own section, and it's a very important section. Okay, have a nice day for now, and I'll see you all next time.